Hello, Satya, and welcome. In this video, we will explore the fundamental relationship between a function and its derivatives. This is a core topic in IB mathematics, analysis and approaches higher level. By the end of this session, you will be able to use the first and second derivatives to analyze the key features of a function's graph, including intervals of increase and decrease, stationary points, and points of inflection. Let's begin by reviewing the properties of derivatives that we will be using. First, the sign of the first derivative, f prime of x, tells us whether the original function f of x is increasing or decreasing. If f prime of x is positive, the function is increasing. If it's negative, the function is decreasing. Second, the zeros of the first derivative, where f prime of x equals 0, indicate the x-coordinates of stationary points. These are points where the tangent to the curve is horizontal. Third, the sign of the second derivative, f double prime of x, tells us about the concavity of the function. If f double prime of x is positive, the function is concave up like a cup. If it's negative, the function is concave down like a frown. Finally, the zeros of the second derivative, where f double prime of x equals 0, indicate potential points of inflection. A point of inflection is a point where the concavity of the function changes, from concave up to concave down, or vice versa. It's crucial to check that the sign of f double prime of x actually changes at that point. Let's apply these concepts to a specific example. We will find the point of inflection for the function y equals arcsin of x. Our objective here is to find the point where the concavity of the function changes. To do this, we need to find the second derivative, y double prime. First, let's find the first derivative, y prime. The derivative of arcsin of x is 1 over the square root of 1 minus x squared. Now we need to differentiate this expression to find the second derivative. It's often easier to rewrite the first derivative using negative exponents. So y prime can be written as 1 minus x squared, all to the power of negative 1/2. We can now use the chain rule to find the second derivative. A double prime is negative 1/2 times 1 minus x squared to the power of negative 3/2, multiplied by the derivative of the inside function, which is negative 2x. Let's simplify this expression. The negative 1/2 and negative 2x multiply to give x. The term with the negative exponent moves to the denominator. So y double prime equals x over the quantity 1 minus x squared, all to the power of 3/2. To find the point of inflection, we set the second derivative equal to 0. Setting e double prime to 0 gives us x over 1 minus x squared to the 3/2 equals 0. This equation is true only when the numerator is 0, so x equals 0. We must now check if the concavity actually changes at x equals 0. We can do this by testing the sign of y double prime on either side of x equals 0. Let's test a value slightly less than 0, say x equals negative 0.5. Y double prime is negative 0.5 over a positive number, which is negative. This means the function is concave down for x less than 0. Now let's test a value slightly greater than 0, say x equals 0.5. Y double prime is positive 0.5 over a positive number, which is positive. This means the function is concave up for x greater than 0. Since the concavity changes from concave down to concave up at x equals 0, we have a point of inflection there. To find the full coordinates, we substitute x equals 0 back into the original function by equals arcsin of 0, which is 0. Therefore, the point of inflection is at the origin, 0, 0. So, we have successfully found the point of inflection for y equals arcsin of x by finding the second derivative, setting it to 0, and verifying the change in concavity. Now, let's tackle another example. Finding the point of inflection for y equals arctan of the quantity x minus 1/2. Our goal is the same. Find the point where the concavity of this function changes. Again, we start by finding the first derivative. Using the chain rule, the derivative of arctan of u is 1 over 1 plus u squared times u prime. Here u is x minus 1/2, and u prime is 1. So y prime is 1 over 1 plus the quantity x minus 1/2 squared. To find the second derivative, we'll rewrite y prime using a negative exponent. I prime is equal to 1 plus the quantity x minus 1/2 squared, all to the power of negative 1. Now we apply the chain rule again to find y double prime. I double prime is negative 1 times 1 plus the quantity x minus 1/2 squared to the power of negative 2, multiplied by the derivative of the inside. The derivative of the inside is 2 times the quantity x minus 1/2. Let's simplify this expression. The negative 1 and the 2 multiply to give negative 2. The term with the negative exponent moves to the denominator. So, I double prime is negative 2 times the quantity x minus 1/2, all over 1 plus the quantity x minus 1/2 squared, all squared. To find the point of inflection, we set y double prime equal to 0. Setting the second derivative to 0 means the numerator must be 0. So, negative 2 times the quantity x minus 1/2 equals 0, which implies x equals 1/2. We must verify the concavity changes at x equals 1/2. Let's test a value slightly less than 1/2. Say x equals 0. Y double prime is negative 2 times negative 1/2, which is positive. The denominator is always positive, so y double prime is positive, and the function is concave up. Now, let's test a value slightly greater than 1/2. Say x equals 1. Y double prime is negative 2 times positive 1/2, which is negative. The denominator is positive. So y double prime is negative, and the function is concave down. Since the concavity changes from concave up to concave down at x equals 1/2, we have a point of inflection. We find the y-coordinate by substituting x equals 1/2 into the original function. I equals arctan of 0, which is 0. Therefore, the point of inflection is at 1 tau 0. We have now found the point of inflection for y equals arctan of x minus 1/2, confirming our understanding of the process. Let's now explore the relationship between the graphs of a function, its first derivative, and its second derivative. This is a crucial skill for IBAAHL. Our objective is to be able to sketch the graphs of f prime of x and f double prime of x, given the graph of f of x. Let's consider a general cubic function, f of x. Here is the graph of y equals f of x. Notice its key features: a local minimum at point A, a non-stationary point of inflection at point B, and a stationary point of inflection at point C. Let's analyze these points using our derivative properties. At the local minimum A, the tangent is horizontal, so f prime of x is 0. The function is concave up, so f double prime of x is positive. At the non-stationary point of inflection B, the concavity changes. This means f double prime of x is 0. The tangent is not horizontal, so f prime of x is not 0. At the stationary point of inflection C, the tangent is horizontal, so f prime of x is 0. The concavity also changes, so f double prime of x is 0. Now, let's sketch the graph of the first derivative, f prime of x. We know f prime of x is 0 at A and C, so the graph of f prime of x must cross the x-axis at the x-coordinates of A and C. Between A and C, f of x is increasing, so f prime of x must be positive. To the left of A and to the right of C, f of x is decreasing, so f prime of x must be negative. The point of inflection B on f of x corresponds to a local maximum on f prime of x. This is because the slope of f of x is steepest at B, meaning f prime of x is at its maximum value. Finally, let's sketch the graph of the second derivative, f double prime of x. We know f double prime of x is 0 at B and C, so the graph of f double prime of x must cross the x-axis at the x-coordinates of B and C. To the left of B, f of x is concave down, so f double prime of x is negative. Between B and C, f of x is concave up, so f double prime of x is positive. To the right of C, f of x is concave down, so f double prime of x is negative. By carefully analyzing the properties of the original function, we can accurately sketch its derivatives. This process reinforces the fundamental connections between a function's shape and the signs of its derivatives. Let's work through a concrete example. We will sketch the graphs of f prime of x and f double prime of x for the function f of x equals x squared minus 2x minus 8. Our objective is to apply the principles we just discussed to a specific quadratic function. First, let's find the derivatives. The first derivative, f prime of x, is 2x minus 2. The second derivative, f double prime of x, is 2. Now let's analyze the original function f of x. This is a parabola opening upwards. Its roots are at x equals -2 and x equals 4. The vertex, which is a local minimum, is at x equals 1. Next, let's sketch the graph of the first derivative. F prime of x equals 2x minus 2. This is a straight line with a y-intercept of -2 and a slope of 2. It crosses the x-axis at x equals 1. Let's verify this with the properties of f of x. The local minimum of f of x is at x equals 1. At this point, the tangent is horizontal, so f prime of 1 must be 0. Our graph of f prime of x correctly shows an x-intercept at x equals 1. For x less than 1, f of x is decreasing, and f prime of x is negative. For x greater than 1, f of x is increasing, and f prime of x is positive. This matches our graph of f prime of x. Finally, let's sketch the graph of the second derivative, f double prime of x equals 2. This is a horizontal line at y equals 2. Let's verify this with the properties of f of x. The original function, f of x, is a parabola opening upwards. This means it is concave up for all x. Since f double prime of x is positive for all x, our graph is consistent. There are no points of inflection because f double prime of x is never 0. By sketching the graphs of the function and its derivatives, we can visually confirm the relationships between them. This is a powerful tool for understanding curve properties. Let's try another example. We will sketch the graphs of f prime of x and f double prime of x for the function f of x equals x cubed minus 3x. Our objective is to apply the same process to a cubic function, which will introduce points of inflection. First, let's find the derivatives. The first derivative, f prime of x, is 3x squared minus 3. The second derivative, f double prime of x, is 6. Now let's analyze the original function f of x. This is a cubic function. Its roots are at x equals negative square root of 3, 0, and positive square root of 3. It has a local maximum at x equals -1 and a local minimum at x equals 1. Next, let's sketch the graph of the first derivative. F prime of x equals 3x squared minus 3. This is a parabola opening upwards. Its roots are at x equals -1 and x equals 1. Its vertex is at x equals 0. Let's verify this with the properties of f of x. The local maximum and minimum of f of x are at x equals -1 and x equals 1. At these points, the tangent is horizontal, so f prime of x must be 0. Our graph of f prime of x correctly shows x-intercepts at x equals -1 and x equals 1. For x less than -1, f of x is increasing, and f prime of x is positive. Between -1 and 1, f of x is decreasing, and f prime of x is negative. For x greater than 1, f of x is increasing, and f prime of x is positive. This matches our graph of f prime of x. Finally, let's sketch the graph of the second derivative. F double prime of x equals 6, 6. This is a straight line passing through the origin with a slope of 6. Let's verify this with the properties of f of x. The second derivative is 0 at x equals 0. For x less than 0, f double prime of x is negative, so f of x is concave down. For x greater than 0, f double prime of x is positive, so f of x is concave up. Since the concavity changes at x equals 0, this is a point of inflection. Our graph of f double prime of x correctly shows an x-intercept at x equals 0. This example demonstrates how to analyze a cubic function and its derivatives, including identifying stationary points and points of inflection. Now, let's reverse the process. We will be given the graph of the first derivative, f prime of x, and our task is to sketch a possible graph of the original function, f of x. This is a common type of problem in IB exams, as it tests your conceptual understanding of derivatives. Let's look at an example. Here is the graph of y equals f prime of x. Notice the key features of this graph. It crosses the x-axis at x equals -6, x equals 0, and x equals 5. It has a local maximum at x equals -4, and a local minimum at x equals 2.5. Let's use this information to deduce the shape of f of x. First, let's find the stationary points of f of x. Stationary points occur where f(e) prime of x equals 0. From the graph, This happens at x equals -6, x equals 0, and x equals 5. Now let's determine if these are local maxima or minima using the sign of f prime of x. Let's create a sign diagram for f prime of x. For x less than -6, f prime of x is negative, so f of x is decreasing. Between -6 and 0, f prime of x is positive, so f of x is increasing. Between 0 and 5, f prime of x is negative, so f of x is decreasing. For x greater than 5, f prime of x is positive, so f of x is increasing. From the sign diagram, we can see that f of x has a local minimum at x equals -6, a local maximum at x equals 0, and another local minimum at x equals 5. Next, let's find the points of inflection of f of x. These occur where f double prime of x equals 0. Remember, f double prime of x is the derivative of f prime of x. So f double prime of x equals 0, where the slope of the f prime of x graph is 0. This happens at the local maximum and minimum of f prime of x. The local maximum of f prime of x is at x equals -4. The local minimum of f prime of x is at x equals 2.5. These are the x-coordinates of the points of inflection for f of x. Now we have all the information we need to sketch f of x. We know its stationary points and points of inflection. Let's put it all together. We start decreasing to a local minimum at x equals -6. Then we increase to a local maximum at x equals 0. Then we decrease to another local minimum at x equals 5. And finally, we increase again. We also ensure the concavity changes at x equals -4 and x equals 2.5. This process of analyzing the derivative's graph to sketch the original function is a powerful application of calculus. Let's work through one more example of sketching a function from its derivatives, this time using sign diagrams. We are given two sign diagrams, one for the first derivative, g prime of x, and one for the second derivative, g double prime of x. We are also given 3 points that lie on the graph of g of x. Let's start by analyzing the sign diagram for g prime of x. The critical points are at x equals 0 and x equals 4. For x less than 0, g prime of x is negative, so g of x is decreasing. Between 0 and 4, g prime of x is positive, so g of x is increasing. For x greater than 4, g prime of x is negative, so g of x is decreasing. From this, we can conclude that there is a local minimum at x equals 0 and a local maximum at x equals 4. Now let's analyze the sign diagram for g double prime of x. The critical points are at x equals 0 and x equals 2. For x less than 0, g double prime of x is positive, so g of x is concave up. Between 0 and 2, g double prime of x is negative, so g of x is concave down. For x greater than 2, g double prime of x is positive, so g of x is concave up. Since the concavity changes at x equals 0 and x equals 2, these are points of inflection. Now we combine all this information with the given points to sketch the graph. First, let's plot the 3 given points. A at 0, 2, B at 2, 0, and C at 4, 2. We know there's a local minimum at x equals 0. Point A is at 0, 2, so this must be our local minimum. We also know there's a local maximum at x equals 4. Point C is at 4, 2, so this must be our local maximum. We know there are points of inflection at x equals 0 and x equals 2. Point A is at x equals 0, so it's both a local minimum and a point of inflection. Point B is at x equals 2, so it's a point of inflection. Now we can draw the curve. It starts decreasing and concave up, hits the local minimum and inflection point at A. Then it increases and is concave down, passes through the inflection point at B. Then it continues increasing and is concave up, hits the local maximum at C. Finally, it decreases and is concave up. This example shows how to synthesize information from multiple sources, sign diagrams and specific points, to construct a complete and accurate sketch of a function. To solidify your understanding, here are 5 practice questions in the style of IBAA-HL. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Find the coordinates of the point of inflection for the function f of x equals x to the power of 4 minus 4x cubed. Question 2. The graph of the derivative of a function f prime of x is shown. Sketch a possible graph of the original function, f of x, clearly indicating any stationary points and points of inflection. Question 3. A function g of x has a local maximum at x equals 1 and a local minimum at x equals 3. Its second derivative is g double prime of x equals 6x minus 12. Find the x-coordinate of the point of inflection. Question 4. The sign diagrams for the first and second derivatives of a function h of x are given. Sketch a possible graph of h of x, labeling any stationary points and points of inflection. Question 5. Consider the function k of x equals x times e to the power of negative x. Find the coordinates of the point of inflection. Welcome back. Let's go through the solutions to the practice questions. Solution to question 1. We need to find the point of inflection for f of x equals x to the power of 4 minus 4x cubed. First, we find the derivatives. F prime of x is 4x cubed minus 12x squared. F double prime of x is 12x squared minus 24. Next, we set the second derivative to 0. Factoring gives 12 on x times the quantity x minus 2 equals 0. This gives potential inflection points at x equals 0, 0 and x equals 2. We test the concavity. For x less than 0, f double prime is positive. Between 0 and 2, f double prime is negative. For x greater than 2, f double prime is positive. Since the concavity changes at both x equals 0 and x equals 2, both are points of inflection. We find the y-coordinates. F of 0 is 0, and f of 2 is negative 16. So the points of inflection are 0, 0, and 2. Let's move on to the solution for question 2. Solution to question 2. We are given the graph of f prime of x, which is a downward opening parabola with roots at x equals negative 2 and x equals 4. First, stationary points occur where f prime of x equals 0. This happens at x equals negative 2 and x equals 4. Let's analyze the sign of f prime of x. For x less than negative 2, f prime of x is negative, so f of x is decreasing. Between negative 2 and 4, f prime of x is positive, so f of x is increasing. For x greater than 4, f prime of x is negative, so f of x is decreasing. This means f of x has a local minimum at x equals negative 2 and a local maximum at x equals 4. Next, points of inflection occur where f double prime of x equals 0, which is where the slope of f prime of x is 0. This happens at the vertex of the parabola, which is at x equals 1. Now we can sketch f of x. It decreases to a local minimum at x equals negative 2, increases to a local maximum at x equals 4, and decreases again. It has a point of inflection at x equals 1. Here is the solution for question 3. Solution to question 3. We are given that g of x has a local maximum at x equals 1 and a local minimum at x equals 3. We are also given its second derivative, g double prime of x equals 6x minus 12. We need to find the x-coordinate of the point of inflection. This occurs where g double prime of x equals 0. Setting the second derivative to 0 gives 6x minus 12 equals 0. Solving for x, we get x equals 2. We should verify that the concavity changes at x equals 2. For x less than 2, g double prime of x is negative, so g of x is concave down. For x greater than 2, g double prime of x is positive, so g of x is concave up. Since the concavity changes, x equals 2 is indeed the x-coordinate of a point of inflection. Notice that the information about the local maximum and minimum was not strictly necessary to solve this problem, but it is consistent with our finding. A cubic function with a local max at x1 and a local min at x3 would have its inflection point exactly in the middle at x2. Let's look at the solution for question 4. Solution to question 4. We are given sign diagrams for h prime of x and h double prime of x. First, let's analyze h prime of x. H prime of x is 0 at x equals 0 and x equals 2. The sign changes from negative to positive at x equals 0, so it's a local minimum. The sign changes from positive to negative at x equals 2, so it's a local maximum. Next, let's analyze h double prime of x. H double prime of x is 0 at x equals 1. The sign changes from positive to negative at x equals 1, so it's a point of inflection. Now we can sketch the graph of h of x. The function decreases to a local minimum at x equals 0. Then it increases, passing through a point of inflection at x equals 1, where the concavity changes from up to down. It continues increasing to a local maximum at x equals 2, and then decreases again. Finally, let's go through the solution for question 5. Solution to question 5. We need to find the point of inflection for k of x equals x times e to the power of negative x. This requires the product rule. First, let's find the first derivative, k prime of x. K prime of x is 1 times e to the negative x, plus x times negative e to the negative x. Factoring out e to the negative x gives k prime of x equals e to the negative x times the quantity 1 minus x. Now we find the second derivative, double prime of x, using the product rule again. K double prime of x is negative e to the negative x times the quantity 1 minus x, plus e to the negative x times negative 1. Factoring out negative e to the negative x gives k double prime of x equals negative e to the negative x times the quantity 2 minus x. To find the point of inflection, we set k double prime of x to 0. Setting the second derivative to 0 gives negative e to the negative x times the quantity 2 minus x equals 0. Since e to the negative x is never 0, we must have 2 minus x equals 0, which means x equals 2. We verify the concavity changes at x equals 2. For x less than 2, k double prime of x is negative, so k of x is concave down. For x greater than 2, k double prime of x is positive, so k of x is concave up. The concavity changes, so x equals 2 is an inflection point. We find the y-coordinate by substituting x equals 2 into the original function. K of 2 is 2 times e to the negative 2, so the point of inflection is 2e to the negative 2. That concludes our exploration of understanding functions and their derivatives. We have seen how the first and second derivatives provide powerful tools for analyzing the behavior of a function. We have learned to use the sign of the first derivative to determine where a function is increasing or decreasing, and its zeros to find stationary points. We have also used the sign of the second derivative to determine concavity, and its zeros to find points of inflection. Furthermore, we have practiced sketching the graphs of derivatives from a function's graph, and sketching a function's graph from its derivatives or sign diagrams. These skills are essential for success in IB/AHL. Keep practicing these concepts with various functions. Thank you for watching.